pick them up at the end of class. So as I mentioned on Wednesday, the project 3 has been handed out. Get that in the end of class?
Oh, I don't.
Nah. So project 3 has been posted, and what I'm going to be spending most of my time on today is, don't worry, I'm about to plug in. Going over the project. So I hope that many of you have had the opportunity to at least look at the project handout. If not, it's not the end of the world. So I suggest that sometime before the end of the weekend, you take a look at it while my comments are still fresh, so that you can sort of understand what's going on. So, before I dive into that, any particular questions on homework material or lecture material? Sure.
Does the differential mode gain have to stay relatively constant over the output swing?
Okay, so let me actually, with regards to the projects, I'll start stepping through that stuff. So I'm going to hold off on that question for right now. Any other questions about the lecture material or the homework 3? No? I know homework 3 was long. We learned exactly how many pages it took you when we went into the homework box, and the stack was around yay big. So, well, it was a long homework. Can we rotate the camera to get this square? Great. EE140 section. You guys hopefully all know my name and email address by now. So, anyhow, what I wanted to do real briefly was just draw some of the problems in Razavi, some of those small signal ones. Well, I guess the question is, a lot of people were saying that homework 3 took an incredible amount of time, and which part or parts would you say were the most time-consuming? 2, so the Razavi problems? And number 1. I mean, yes, the fact of the matter is that using Spice until you're comfortable with it, that'll take time. And there aren't really any shortcuts, there aren't any concepts, so to speak, aside from just being more comfortable with the tool, that'll help you complete problems like that any faster. But problem 2, which is the Razavi problems, I took a look at them and sort of wanted to give you some insight as to how some of these might be completed a little quicker. So, one of the problems, I think it was part A, looked like this. M3, M2. So these are all biases. VI, M1, V out. So that was, oops, and this is connected to power. And the question is, what is V out over VI? Now, what you can always do is you can always do the brute force small signal model. Explode each of these devices out into a transconductor or resistance and blah, 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 blah. All that other stuff. But hopefully, what you'll start to get the intuition about is how simplifications and sort of substitutions can be made. And when I look at this problem, I see a clear shortcut. Okay? Does anyone have any suggestions as to what kind of shortcut might be taken with this kind of circuit? Yeah?
Change that to a resistor on top.
Exactly. So looking up here, we can say this is an effective resistor, M2 and M3, M2 degenerated by M3, right? So, and the basic goal is that once we replace this with a resistor, then the rest of the stage is, so then what it looks like is a single transistor amplifier, M1 R effective, VI, V out. And this is easy. Okay, this is less difficult. Hopefully this is easy-ish, because what kind of stage is this? Common gate. Okay, so the single transistor amplifiers, it's really important that you understand them and really, really, really can look at them and sort of identify how to calculate gain or input resistance or an output resistance and stuff like that. Okay, so basically what we can do here is that we can calculate what R effective is, right? So in order to solve this problem, this is the first step, but sort of the intermediate step is calculating what R effective is. Now, can anyone immediately identify how to go about solving that easily? Does it look like any particular topology? I see. Yes. You want to give it a shot?
I just know it's a source-degenerated resistance.
Exactly. So what you can do there is you can say, oh, M3. That M3 just looks like an R out 3, and then we've got this, right? And we're saying what's the resistance looking up there? That's just a source-degenerated common source stage, and that's, so this is M2. So R effective is approximately, and I'm dropping out some of the smaller terms, GM2 RO2 RO3. Yeah.
Were you allowed to drop out terms of the homework though? Because I don't know like how much.
Yeah, that's a good question, and I apologize that we haven't made some of that stuff perfectly clear. Saurabh was the one who made this homework, so ultimately he decides. But as far as I'm concerned, if you made an approximation like this rather than the full-blown thing, which is 1 plus chi plus RO2 plus RO3, if you start making approximations like that, or even better, if you say this is the R effective and I am ignoring those terms, you can do that here. Like, as long as you're not making incorrect approximations, you're fine. You're fine. And the important thing is that you understand the stuff. And really what it's going to come down to is how well you ultimately do in this class is not going to be a function of how high homework scores you get. It's going to be how well you understand the underlying concepts, so that when the bigger assignments come, like the design project and the exams, you can get through these problems, easily. Okay? So then, so we know what R effective is, and then we just know that, by and large, the gain of common source stage is GM times R out 1 parallel R effective. Plug everything in, boom, 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 you're done. Now, I don't know how long it took you to do this part, but I'm guessing that I did it more quickly than you did. So there's a shortcut. Granted, I also didn't spend all that much time with the math. So that's one. Another one was this. And the nice thing about this is that it forces you, the nice thing about this guy is that there are PMOS devices in it. It forces you to be comfortable with PMOS devices, which was an issue I think we talked about last section. Oops. Did I draw this wrong? VI, V out. M2, M1. Oops. This was like so. M3. Okay, so this was another one. Okay, and so the kinds, what I look at this and I see shortcuts. There are 3 transistors here. 3 transistor circuits are kind of difficult to analyze. Can we reduce anything? What can we reduce? Right, we have 2 diode connected transistors. So we can replace this guy with its effective resistance, which is 1 over GM1. M2 is still there. This is 1 over GM3. Source follower, right? This is a source follower. This is a single transistor stage. This, too, is relatively easy to analyze. Okay? But then, there are some circuits that, well, you know, they're weird, they're ugly, and it's going to require some math. And I'm guessing that this is one that took many of you a while, because I looked at this and I wasn't sure what kind of shortcuts you could take. M1, M2, M3. Okay? So this circuit. How might you go about solving this circuit? Any thoughts? Any thoughts as to what you might try to do to try to, rather, you could put everything into a small circuit. You put all the small circuit equivalents in here. It's kind of hard. Is there anything simpler that you can do? Huh? That's true. Spice will certainly give you a number, but the number won't help. So with this, what I would do is, again, R effective looking up, and then we know that the gain is equal to GM1 times R01 parallel R effective. Now, for R effective, figuring out what R effective is not intuitively obvious, or at least not intuitively obvious to me. Yes?
It's okay to just assume that M3 is in saturation and then just like pretend that it's connected on the top of M2 instead of underneath M2 and then just treat M3 as a resistor? Or is that like assuming too much?
That is assuming way too much, because I think the problem clearly stated that all these devices are in saturation. So if all these devices are in saturation, M2 doesn't look like a resistor between drain and source. There's also that current source thing, that transconductance element going on. So yeah, ideally what you'd like to do is replace this whole thing, this top portion, with 1 over GM3. Doesn't work. Okay, and for this, you actually have to do the small signal model. So what I'm going to do here is I'm actually going to draw what the small signal model looks like, just to show you how I would solve this problem. Okay? Is that something that would be generally useful? Okay. So what we have is now we have a 2-device thing, and the nice thing is that, well, analyzing 2 devices is 1 device easier than analyzing 3 devices. So this is the input node, R effective, right? M2, M3. So now, let's replace, and this is, I'm going to label these nodes explicitly. This is gate 2. This is node X. This is, I'm calling node A. Okay? So let's start with M2. M2, the gate 2 node is here. It is connected to a small signal ground. The source node is node X, where you're going to insert your test current. You've got GM2, VGS2, R out 2. This is node A. Node A is also connected to the drain of the PMOS source. And as we discussed before, a PMOS small signal model looks identical to an NMOS small signal model. So the gate of the NMOS, of the PMOS, is here. The source is VDD, which is a small signal ground. Okay. there's a current flowing from the drain, which is node A, and similarly, there's that. Okay? This is the small signal model. And then in here, this is node X, node A, node G2. We're going to be inserting a test current IX and measuring VX. Okay? So does everyone understand how I got to this small signal model? Are there any questions about this? Okay. Being able to go from here to here when you have to is important. Practice it. Do some if you're not comfortable with it, draw a couple of devices on a piece of paper like this in some weird topology and practice drawing this because it will help you. So now let's make some simplifications. Okay? VGS2 equals minus Vx because the gate node is tied to ground. Okay? So therefore, this device here is basically equivalent to doing GM2 Vx. Okay? So in my equations, I'm going to replace that. Similarly, VGS3 is equal to positive Vx. See that? Because it's from Vx to ground. So this is Vx. Now let's do KCL. So here's a node here. So going into this node, the current going into this node is, can everyone see everything? Yeah, good. Going into the node is Ix. Coming out of the node is the current through this transconductance device, which is equal to GM2 Vx. And notice that because the polarity is outward, the sign here is positive because I'm putting it on the other side of the equation, plus Vx minus Va over RO2. That's the current flowing through here. So basically what this KCL is, the current flowing in is equal to the current flowing through this transconductance device plus the current flowing there. Okay? So that's KCL at X. And then KCL at node A here. Okay. What do we know? Can anyone tell me what the current flowing across this branch is? Ix, exactly. You could say it's equal to the current here plus the current here, but because this current branches out and then merges back here, this current also has to equal Ix. So then Ix is equal to the current flowing out, which is GM3 Vx, plus the current through this, which is Va over RO3. Now, because I want to get to the project and start talking about that, I'm not going to solve these equations. Okay? Solving these equations are relatively straightforward, and you can end up getting Vx over Ix is equal to R effective, and then the gain itself is equal to GM1 times RO1 parallel R effective. Okay. So I've set up the problem for you. I didn't turn the crank all the way through, but that's because I think it will be much more beneficial to you guys if we talk about the project from here on out. Okay? So that's basically an explanation as to how to go about looking at transistor topologies and making the required simplifications to make things simpler, and also having a basic level of comfort with the small signal model. You know, converting into the small signal model and just solving using algebra. All right. So, can we zoom in tight so that they can actually see the text? Zoom into the page width, little further out. There we go. Great. All right. So this is design problem 1. Okay. Show of hands, how many people have had the chance to at least glance at it? Fantastic. So most of you. That's great to hear. It's due in 2 weeks, as we said before. It probably makes sense to start thinking about it. Okay. So what I want to do is walk you through the design project as well as the infrastructure that we have for doing this design project, so you understand what's going on. So first things first, what are you actually designing? You're designing this block, this amplifier. It is a single-ended to differential amplifier. Excuse me, differential to single-ended amplifier. It has a positive input node, a negative input node, and a single output node. Okay? So therefore, in addition to providing gain, there has to be some way that you convert the output voltage, the input differential voltage into an output voltage. Okay? And we'll talk about how one might do that a little later on. So in addition, this amplifier is also driving a resistance. Now this resistance should not be in your circuit. It will be provided by what we call test benches, and I'll get into that a little later on. But what you're going to do is you're just going to design the internals of this circuit as like a sub-circuit block, so that when we test it, we can take your sub-circuit, drop it into what we call a test bench that connects all the pins up appropriately and provides this load and runs a series of tests on it. Okay? So, getting back to the design specifications. First note, individual projects. Each person has to hand in their own report. So let's look at the specifications here. So first off, there's an L min and a W min. And what that basically means is you're designing your transistors. You get to size your transistors. You get to pick the sizes. This is a 0.13 micron process, and this process has certain design rules. Devices cannot be fabricated that have a length of less than 0.13 microns and a width of less than 0.15 microns. Okay? Pretty straightforward. The other constraint is that all your lengths and widths must be integer multiples of 0.01 microns. And that's simply because in real processes that's what you'd have to do. Additionally, what we've seen in past years is that people tweak like the 6th decimal point of their width or length of their device sizes in order to tweak out their performance. And in reality, you don't get that kind of precision. So relying on that is kind of cheating. It's not something that would actually happen. Okay? So you have, moving along, you have a positive supply and a negative supply. The positive supply is a 1.2 volt supply, which also you don't need to put in your circuit. It will be provided by the test bench. Negative supply is ground. Okay? So it has to drive a 1 kilo ohm resistance, and as I mentioned, don't include this device in your schematics. And so now here, that's kind of like the test setup. This stuff down here are the actual real specs. So let me move that up a little bit. Okay? So there are two specs of primary importance: differential mode gain and common mode gain. Okay? And the differential mode gain is defined as V out over the input differential voltage. So it's a little different from what Bob mentioned in class, where you have VIP. What Bob had was differential in, differential out. And so there's an input common mode and an input differential mode, and an output differential mode and an output common mode. Okay? For this block, as Bob mentioned, the differential mode gain is defined as VOD over VID. And the common mode gain is defined as VOC over VIC. Okay? That's not what we're actually dealing with. Can we zoom out just a touch? Great. What we have is a block that looks like this: VIP, VIN, and Vout. This has a differential and a common mode input, but there's only a single output voltage. So here, the gain is defined as Vout over VID, and it's really the partial derivative of Vout. It's the gain. It's that slope the change in output voltage for a small change in input voltage. And the common mode gain is defined as dV out over dVIC. Okay. Does that make sense to everyone? Any questions about that? Like what these specs mean in this sense? Okay. No. All right, so getting back to here. Can we zoom? Thank you. So the differential mode gain has to be greater than 1,000, okay? And the common mode gain has to be less than 0.1. So that means that, obviously, the differential mode gain is a heck of a lot higher than the common mode gain. So topologies that work have to be ones that have a high common mode rejection. In other words, where the differential mode gain is higher than the common mode gain. And I'll work through an example of that in just a second. So the next specification, VICM max minus VICM min. Okay? So what you get to, that has to be at greater than 0.5 volts. And what that means is that you get to specify, so let me draw this as VIP, VIN. So the usual way we draw this is that this has positive VID over 2, this has negative VID over 2, okay, yeah. So you get to specify what the DC bias for VIC nominal is. You tell us that in your circuit with a dot parameter. So let's say you were to say my nominal input common mode is 600 millivolts. Okay, you tell me that. So that means what we're going to do is we're going to test your circuit. We're going to test these specs, ADM and ACM, with this, ACM, ADM tested, and then with a DC bias. And notice that I've started drawing it with all caps. VIC high is equal to 850 millivolts, and VIC low is equal to 350 millivolts. So over all three of these corners, your differential mode gain and your common mode gain specs have to be met. Okay? That means that there's a relatively large input common mode range requirement on your amplifier. Okay? So that's this. Okay. And so what we do here, and you'll see this in the test benches that I'll talk about a little later, is that we do, you do that .tf statement, which figures out the gain, and we apply this common mode, and then we do a .tf with, Vout versus VID, where VID is, related to here. Oops. To see what the differential mode gain is of the circuit at each of these three bias points. Okay? So that's that spec. And then moving down, can we zoom in tight again? Great.
Questions?
Yes.
So does that mean like when we test the VIC with the high value and low value, the differential mode gain will have to greater than 1,000, and do they have to like approximately equal, or
no?
They just...
We removed the equality spec, so you could hypothetically design a very high gain amplifier where when you move the common mode up a little bit or down a little bit, all of a sudden the gain drops in half. But if it drops in half from 10,000 to 5,000, that's okay. But if you're designing an amplifier like that, then it's probably not optimal in some other characteristic, because getting a gain of 10,000 is overkill. So a good design will keep those gains relatively close, but there is not a specific specification. Okay? Any other questions? All right. So The next specification is V out peak to peak. So basically, what that means is that similarly with this VCM swing, what we're going to do is minus. You're going to give us your VIC, and our test bench will figure out. So this resistor goes to 600 millivolts. If you look on the schematic, this is 1K ohm. Our test bench will figure out what voltage to apply to get this guy to 300 millivolts, 600 millivolts, and 900 millivolts. Okay? So we've got some funky test benches in here that'll do that for you. And what you need to do is make sure that the gain at each of these bias points, in other words, the small signal gain at each of these bias points, is still greater than 1,000. So what that means is that so VID equals 0. So what that means is that the actual VID versus V out. The actual large signal transfer function will look something like this. Okay, and this is 600 millivolts. This is 900 millivolts. This is 300 millivolts. Basically what we're doing is we're setting up the DC VID, all caps, to get to each of these points, and then using some analysis to see what the slope is here. And the slope here, which is the slope, is equal to the small signal gain. And we're checking to make sure that that's higher than 1,000. Okay? Does that make sense to everybody? Okay. So that's that spec. Did I give you enough time to copy this down? Do you need this up here a little longer? Okay. All right. So I'm going to move along now. So the other specs on this sheet are area and power. And those specs you want to minimize because, as it shows down here, the overall goal of this design is to meet all those specifications while minimizing the product of power and area. Okay? And by area, we mean gate area. So it's the WL product. It's the sum of all the W times L's of all your devices. So if your device were a 2-transistor amplifier, where this was W equals 1 micron, L equals 10 microns, and then this guy were like 20 by 20, 20 over 20, 20 micron L, 20 micron W, then the total area would be 400 microns squared for this device and 10 microns squared for that device. So your area would be 410, and the power would be however much current you dissipate times 1.2 volts. Okay? And we have scripts that calculate that and calculate the FOM. Yeah?
What's the typical FOM that you guys are looking for?
As good as you can do. It's a good question. That's what design's all about, figuring out how good you can do. Now, jumping ahead, because I know that you're always very concerned about how these things are scored. Let's look at this. Grading. This is the last section, the last page of the design handout as opposed to the addendum. 100 points total. We want you to write a good report. And the importance about this report is showing us, convincing us how you went through your analysis to choose what you did. Realistically, it's more important that the circuit that you design behaves exactly as you expect it to than you have the greatest circuit in the world and the lowest power, but you have no idea how you came up with it. Okay? So, and actually chances are, I mean, I need to talk to the professor about this, and he's been out of town. The points are going to be allocated a little differently. And I would say put a little bit more emphasis on explaining your analysis clearly. Okay? So then there's some points on specifications, and then some points on how well the FOM is minimized, and then basically some extra slot points, so to speak, that gives the TAs some leeway in deciding, the gut sense of how good your design is, whether or not you slap stuff together. And this kind of goes back to your analysis. If your analysis is real tight and it behaves exactly how you expect it to, then your design is really robust, and you'll get a good score here. If it's not clear the connection between your performance and your design and your analysis, then it's not a particularly robust design. It happens to work, bravo for you, but it doesn't seem particularly repeatable, and it might be that it's not so robust. And additionally, some originality. If you come up with some interesting ideas as to how to meet these specs while minimizing the figure of merit, great, more power to you. You teach us something, and you get some extra points for that. So that's the grading. The other thing is that we are providing a whole lot of test infrastructure to you. We're providing test benches and a script that enable you to run the tests that we're going to run to make sure that your circuit works. Okay. In addition to that, there's an example circuit that I have that you can use the test benches on. Now, granted, this example circuit that I put together doesn't have transistors. It has ideal voltage sources. I have a design. I did this design, so just to make sure that the spec could be met. But this is just for you to understand how to use the test infrastructure. Okay, so if you hand back a design that looks suspiciously like that design, you're in big trouble. And in particular, what's really important is that part of the design project includes coming up with the biasing scheme, generating your current biases. And I talked a little bit about that on Wednesday. Bob's going to continue to talk about that on Monday. In your subcircuit, you have no ideal sources. If there are any V's, I's, E's, J's, H's, K's, then that's problematic. You've really got to let us know why you're doing that, and that's not good because you don't have batteries available to you on chat, like 1 millivolt batteries. So really, unless you're absolutely hosed and you need this to get around something, don't use it. You will be your score will be docked because that's kind of cheating. Okay, let me think what else I want to cover. So any questions about sort of the overall structure of the project? Yes.
About a FOM thingy, you said we have to minimize,
yes.
Right? And then when we try to use the resistor, but we usually just put in R1 between what node is what ohm. How can we calculate the area? Good
question. That's a fantastic question, and it's explained in the area calculation. You just put down the resistance. Basically, there's a certain amount of area per ohm or per kilo ohm that a resistor will take. That's automatically calculated by us. Just indicate the resistor, but understand that bigger resistors, if you double the resistance, it'll double the area. Okay. You can go in. It's all explained in the area calculation section. Okay. And it talks about ohms per square. So the report guidelines are there's 3 things on the website: the actual design problem, a guideline document, and a zip file with the various test bench stuff. So read the report guidelines and the circuit submission guidelines. Read the important caveats. Read the information about how to use the test benches and the test bench processing, because it will help you out. But at the same time, these automated test benches, basically, you have your circuit, you enter in this command, and it'll report for you all the various gains at various points. We strongly suggest that you do not use that script as your design methodology. Because trust me, it will take you an incredibly long time to tweak everything to meet all the specs. Use hand analysis. So that gets back to the actual project. So we've got, the question is, this is a design project. How do you go from these specs to an actual transistor implementation? And there are a couple of different tasks that are really useful to do. And you can sort of do them top down or bottom up. I'm going to start listing them from the bottom up, but if you feel more comfortable doing it top down, that's fine. So one is device characterization. And what does that involve? That involves looking at the model deck that we give you, which is right here, and you have that in the zip file. Extract mu naught, k prime, vt gamma, dot, 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 as well as lambda, to get all your model parameters. Okay, your level. These are all level 1.
We need to extract mu naught.
You don't have to. I mean, mu naught times Cox is k prime. So that's one thing you can do. Along those lines, you'll notice actually, and we talk about this in the handout, that on the, can you see this text? Great. Right here. That lambda is not a constant. Lambda is an expression, and lambda actually equals some, I'll call it lambda naught times exponential of L naught over L minus 1. If you actually, this is a simplification. This is doing some algebraic simplification to make things more simple, more obvious. But that's basically what lambda is. So lambda is now a function of your actual device length. And you can see that L naught is 0.13 micron, 0.13 micron. So as L increases, L naught, lambda naught, it does something like this. And this is L naught over exp1. So by increasing L, you decrease your lambda, which increases your output resistance, but increases your area. So it helps you meet the gain specifications, right? But there's an area penalty. So you kind of have to figure out what L's to use. And it ends up being strongly diminishing returns, because even as L goes to infinity, lambda asymptotes out. Okay? Another thing to keep in mind is that these are the models we're giving you are actually level 2 models, not level. These are level 2 models. And what the level 2 models are used to do, and you'll remember this from homework 1, is that they're used to model subthreshold. Because this is something I went over in office hours a couple of weeks ago. Let's do a real quick calculation as to what the gain of a transistor, GM times R out, is as a function of the device current. So that's the only thing you're changing. Okay? So if we assume square law model, if we assume level 1, GM in terms of ID is equal to the square root of 2k prime W over L ID. So GM is proportional to root ID. R out is equal to 1 over lambda ID, is proportional to 1 over ID. So that means GMR out of level 1, and I'm going to draw this in a log-log plot so that the square root relationship. So this is proportional to 1 over root ID, GMR out, looks like that with a slope of minus 1/2. Okay? So that means hypothetically, if you were to decrease the drain current lower and lower and lower and lower and lower, your gain would be going higher and higher and higher ad infinitum. So out of one device, you could get a gain, hypothetically, of 1 trillion, 1 billion, whatever you wanted, and you'd be doing it at almost no power. That's not real life behavior, because real life behavior is level 2, or level 2 gets a little closer, is that as ID gets lower, so GM as ID goes to 0, now it begins to look like a bipolar. It looks like ID over N times V thermal. V thermal is KT over Q, which is approximately 25.8 millivolts. Okay? You might remember this from your bipolar device characterization. So what that means, let me move that to here, is that GM R out in level 2 for ID big is proportional to 1 over root ID, because it's square law. Oh, sorry. Level 2. GM R out ID big looks like square law, so it's proportional to 1 over root ID. But GM times R out ID small becomes a constant, because this is proportional to ID, and this becomes proportional to 1 over ID. So basically, in level 2, log ID log GM times R out, it looks like this, or something approximately like that. 1/2, and then a slope of 0. Okay? So it's useful to figure out where sort of this cross point is, going from here to here, and where you want to design in order to minimize power, but also minimize area without losing performance. Okay? So yeah, that's the end of section. It's noon. I'm more than happy, as per usual, to stay here till 12:30 to continue talking about the project if you want to. By all means, feel no obligation to go. Homeworks are right here. Or feel no obligation to stay. That's what I meant to say. And homeworks are right there. I'm going to continue talking about the project.
Well, could you go get the homework up there or bother?
No. I mean, let's 5-minute break regardless. Yeah. Well, so here's the thing: if you're in subthreshold, subthreshold is still saturation. It's not. It's a type of saturation, right? Um, so subthreshold means that your GM is different than what you would expect it to be in the square law, right? Might it be easier if why don't we start passing them around? Like grab a pile. Yeah, just hold on. Grab a pile, distribute it around. We've got too many people around here. So grab a pile, distribute it around. Make sure all the copies end up in that back corner when you're done. And also, please make sure, hey guys, listen up for a second. Subsequent homeworks, put the section you attend on the top of the homework. Put Friday, David, or Tuesday, Sorab, at the top of the homework. Okay. Yeah. What is GM proportional to? Okay, and what is RO proportional to? Yep. Okay. question? Level two allows for subthreshold, among other things. 1 second. Okay. You have to go. Yeah. Okay. Yeah. It's hard to figure out. I'm still learning how much I can fit in an hour. So bear with me. If you can come to office hours beforehand, the 10 to 11 slot, like I spent the entire hour talking about the project, and we covered an incredible amount of material. I imagine that's what we'll do next week as well. Okay? Yeah.
I was just wondering for a concept to understand if we should keep people up to have enough expertise to kind of build in some consistency.
Um.
That way I could use the source follower on the side. Because the threshold is like 300, right?
Yeah.
So on the output stage, if we had 300 versus 25%, then we could increase the threshold a lot more. Even if
Right.
it's
But
good.
there are other ways to do it, and you can do a high swing output stage, or you can figure out. So what's okay? So what you do, what you're doing. This is interesting. This is something I haven't seen before. What do you what are you trying to do here?
Use the VT point here to bias these current sources, and then this is like a common source that
Right.
we use to cascode the output.
But this is the output.
Yeah, and then it's basically different.
So I see. Oh, so you're sort of doing a push-pull here as well. You might actually want to hold on a second. You might actually doing it this way. You might actually want to keep this stage fully differential. Bias this cascode appropriately. It's hard because then you need to get the
Okay.
um because you're using this. This is sort of a pseudo differential stage. It's almost differential. There's positive signal here, negative signal there. It's the gain to here and the gain to here are not symmetric. You realize that.
Where?
All right. Well, let's talk about because the res, because the gain to here, the gain to here and the gain, the gain to here and the gain to here are not
They're the
anti-symmetric.
same.
But this has a low impedance. This is a low impedance node.
So if I just biased it
If you
instead.
biased it instead, yeah, and I think there are probably simpler things you can do than this. Yeah, I mean, why do you need to cascode it? Because there's still just R out up this way, and you're comparing it to GM R out, R out. This is going to be so much
Big
bigger.
enough. Okay.
Like a single R out should be enough. All right.
The our amp, will load the circuit.
It will load the circuit.
So having all this space out, we don't want to
It can, well,
clog up.
it depends on your output stage. If you use a common source, you don't need to use a source follower for this project. And actually, you can't because a source follower you'll lose the VT, so you won't be able to get the swing.
What happens if we use a follower gain?
Well, you will, but so the gain of that output will be GMRL. The last stage will be GMRL rather than GMR out, right? So,
Right. So
sure.
what are the characterizations that go into delivering input versus output?
You should always. I mean, you can't. If you make an assumption that a device is in saturation, I mean, we've said this enough in class, and that's what Bob has mentioned this enough in lecture. It wasn't meant to. Don't worry about it. It's a point. I mean, like,
It's like two points.
well, a point for each transistor you didn't check. It's not the end of the world. All
Okay.
right, Josh, you'll be fine. Okay. The important thing is to understand it.
Okay.
Sure.
What question?
See, but I need to look at this. Okay. It's let's talk about this later. Nikhil Sharma, his name is on the webpage. Email him and CCing both PAs. Okay. All right. Yes. Okay. All right. so I'm going to continue on for a little while. All right. No problem. So, we were talking about the first step in this design process, which is device characterization. And a question was asked during break, do you need to really do sub-threshold okay. So do you need to do sub-threshold calculation in your hand calculation? Now, the thing to keep in mind is that if your device is in sub-threshold, then your GM is going to be dictated by that equation. So in order to understand how the circuit is going to behave, you should know what your GM is. Therefore, you should calculate, if you think your device is biased in sub-threshold, you should calculate what your GM is. So I get the short answer is yes. There's one little issue here, and that is that the level 2 model is not perfect in terms of modeling sub-threshold. And you will certainly get extra credit if you point out what the problem with this particular model is, if you happen to stumble upon it. Don't worry about it. My suggestion to you is don't model it, don't design the stuff in sub-threshold because your devices will just have to be too big. But yeah, the modeling isn't perfect. So, okay, I guess I'm not on. I'll use the What's that? What's the mean? All right. So, my gain. And if you put